So we have problem number 10 in Advanced Classical Mechanics Practice Final Exam. So let's begin. Heavy symmetric top has moments of inertia. I sub 1 equals I sub 2 does not equal I sub 3. Mass M, center of mass, distance L from the fixed point, and gravitational acceleration G. So part A, write the Lagrangian using Euler angles phi, theta, and psi. Part B, identify cyclic coordinates and conserved momenta. Part C, and some would say cyclic. Part C, derive the effective one-dimensional equation for theta of t. Part D, find the condition for steady precession. And Part E, analyze the stability of steady precession for small perturbations. So this is a rigid body dynamics with Euler angles problem. So for a heavy symmetric top, I sub 1 equals I sub 2 does not equal I sub 3. We let phi, theta, psi be the Euler angles, where theta is the angle between the symmetry axis of the top and upward vertical. The kinetic energy is T equals 1/2 I sub 1 times the quantity theta dot squared plus phi dot squared sine squared theta plus 1/2 I sub 3 quantity psi dot plus phi dot cosine theta. So we have the gravitational potential energy is V equals mgl cosine theta. So the Lagrangian is L equals 1/2 I sub 1 quantity I dot squared plus phi dot squared sine squared theta plus 1/2 I sub 3 quantity psi dot plus phi dot cosine theta quantity squared. Then minusing the mgl cosine theta. So the coordinates phi and psi are cyclic, so their conjugate momenta are conserved. So first here our p sub psi, that is going to equal the partial of L with respect to psi dot, and that equals I sub 3 psi dot plus phi dot cosine theta. So from here, p sub psi equals I sub 3 times this quantity here, psi dot plus phi dot cosine theta equals constant. Okay, so, and this I3 was distributed to both of these here. So, so this is the angular momentum component along the symmetry axis of the top. And here for next, this P sub phi equals partial of L with respect to psi dot. I'm sorry, this P sub phi equals the partial of L with respect to phi dot. And so P sub phi equals I sub 1 phi dot sine squared theta plus P sub psi cosine theta, and that's going to come out equal to a constant. This is the angular component along the fixed along the space fixed vertical axis. So solving for phi, P sub phi minus P sub psi cosine theta equals I sub 1 phi dot sine squared theta. So isolating this phi dot, that equals P sub phi minus P sub psi cosine theta over I sub 1 sine squared theta. So also P sub psi, that equals I sub 3 times the quantity psi dot plus phi dot cosine theta. So psi dot equals P sub psi over I sub 3 minus phi dot cosine theta. And the conserved energy here is going to be E equals 1/2 I sub 1 theta dot squared plus 1/2 I sub 1 phi dot squared sine squared theta plus 1/2 I sub 3 quantity phi dot plus, quantity psi dot plus phi cosine theta, that quantity squared, and then adding mgl cosine theta. So substituting the conserved momenta, since I sub 3 parentheses psi dot plus phi dot cosine theta close parentheses equals p sub psi. So from there we could say that 1/2 I sub 3 parentheses psi dot plus phi dot cosine theta close parentheses raised to the second, that's going to equal the following: p sub psi squared over 2I sub 3. So also from here, 1/2 I sub 1 phi dot squared sine squared theta, that's going to equal the quantity p sub phi minus p sub psi cosine theta squared over 2I sub 1 sine squared theta. So E equals 1/2 I sub 1 theta dot squared plus this quantity here, this numerator, p in parentheses p sub phi minus p sub psi cosine theta close parentheses squared over 2I sub 1 plus p sub psi squared over 2I sub 3 plus the mgl cosine theta. So the motion in theta reduces to a one-dimensional effective problem. 1/2 I sub 1 theta dot squared plus u sub EFF of theta equals E, where u sub EFF of theta equals this quantity p sub phi minus p sub psi cosine theta squared divided by divided by 2 I sub 1 sine squared theta plus p sub psi squared over 2I sub 3 and then plus mgl cosine theta. So the constant term p sub psi squared divided by 2I sub 3 does not affect theta motion, but it contributes to the total energy. And building on that, for our steady precession here, theta equals theta naught, and that is constant. Therefore, theta dot equals 0, and theta double dot equals 0. So we're going to let phi dot equal capital omega, and then we have psi dot plus phi dot cosine theta naught equals lowercase omega sub 3. And then p sub psi equals I sub 3 lowercase omega cubed. So from the theta Euler Lagrange equation, I sub 1 theta double dot equals I sub 1 phi dot squared sine theta cosine theta minus I sub 3 times the quantity psi dot plus phi dot cosine theta, close parentheses there, phi dot sine theta plus mgl sine theta naught. And for the steady precession here, pardon the condensed version of this, for the steady precession, 0 equals I sub 1 capital omega squared sine theta naught cosine theta naught. So for that first part there, minus I sub 3 lowercase omega sub 3 capital omega sine theta naught, and then plus mgl sine theta naught in that box there. So assuming sine theta naught does not equal 0, we divide by sine theta naught, and then this is going to become I sub 1 capital omega cosine theta naught minus this I sub 3 lowercase omega sub 3 capital omega sine theta naught plus mgl sine theta naught, and that's going to be equal to 0. And since P sub psi equals I sub 3 lowercase omega sub 3, then I sub 1 capital omega squared cosine theta naught minus P sub psi capital omega plus MGL equals 0. And this is the condition for steady precession. So solving for capital omega is going to equal P sub psi plus or minus the square root of P sub psi squared minus 4I sub psi MGL cosine theta naught divided by this 2I sub 1 cosine theta naught. And capital omega is going to be equal to this numerator I sub 3 omega sub 3 plus or minus the square root of I sub 3 squared lowercase omega sub 3 squared minus 4I sub 1 MGL cosine theta naught divided by this 2 I sub 1 cosine theta naught. So for real steady precession solutions, the discriminant must satisfy this P sub psi squared has to be greater than or equal to 4I sub 1 MGL cosine theta naught. And picking up over here, for a rapidly spinning top, P sub psi squared has to be much greater than 4I sub 1 MGL cosine theta naught. So the slow precession branch is approximately capital omega sub slow is approximately MGL over P sub psi, and that equals MGL over I sub 3 lowercase omega sub 3. And this is familiar slow precession rate of a rapidly spinning top. And for stability of steady precession, the fixed value theta naught must correspond to a local minimum of the effective potential U sub EFF double prime, that theta naught has to be greater than 0. So building on that, equally small perturbations, eta of t around theta naught. Theta of t equals theta naught plus eta of t, and they satisfy this I sub 1 eta double dot plus U sub EFF double prime of theta naught eta equals 0. Thus, the small notation frequency is W sub NUT squared. I'm sorry. Thus the small notation frequency is omega sub NUT squared equals U sub EFF double prime of theta naught divided by I sub 1. So our stable steady precession requires lowercase omega sub NUT squared being greater than 0. Therefore, steady precession is linearly stable precisely when the equilibrium angle theta naught corresponds to a local minimum of the effective potential. Okay, so that's all for problem 10. Thank you very much and have a great day.